Hi there, I'm Seth, and in this video, I'm going to show you how to calculate correlations in Excel, SPSS, and R. So let's say we've got some made up data here. 4 people, we have scores on job satisfaction, productivity, and positive affect. Okay, so by the way, I'm not really going to be explaining a lot of the conceptual stuff. I'm assuming that if you're here, you understand that, and now you're looking for, and you even understand the formulas, and now you're looking for how do I make the computer do it swiftly so that I can then use that information. Okay, so to calculate the correlation, let's say we're looking at the relationship between job satisfaction and productivity. You should not base any conclusions on such a small sample size, or at least not any statistical conclusions, but I'm keeping it small for simplicity. So to get the correlation, click into whatever cell you want the result to appear in, say equals, and then start spelling correlation, CORREL, and you can see it knows what I want. It's trying to autocomplete it. I'm working in Windows, so I'll talk about all the commands I mentioned may be specific to Windows, and you may have to adjust a little bit if you're in a Mac. So I can hit tab or open parentheses, and now it wants, for its input, it wants 2 arrays of data because we're going to look at the relationship between 2 sets of scores. So first, we're just going to highlight the job satisfaction scores, comma, highlight the productivity scores, enter. That's our correlation, 0.4797. All right. We could also have said equals correlation and then just click the columns themselves. Excel's smart enough to know what you're trying to do, and it will ignore those labels. So that's also an option. What if we want a correlation matrix? To do this, what I'd recommend is accessing the data analysis tool pack. How do you do that? Well, if you don't already have it, if you've already got it, you'll find it here. You'll click data and you'll see it right here, data analysis. If you don't have it already, you can go to file, down to options, and then down here to add-ins, say manage the add-ins, go. And then make sure that analysis tool pack is checked. And this will give us access to, when we go into the data tab, data analysis. Okay, so we're going to go to correlation. Okay, it wants the input range. So what data are we wanting this for? I'm going to highlight all 3 variables, including their labels. It's not required, but I think I like the output a little better. And I need to let it know, by the way, that first one is a label, it's not a data point. Okay, I want this to show up in the same spreadsheet, so I'm going to say I'm going to specify the output range right here, and then let's say make it appear right here. This should be, or maybe, yeah, no, this is fine. Okay, enter. Let's see, this is a little hard to see, so I'm going to expand these out a bit. Still hard to see. Okay, so we've got a correlation matrix. Excel automatically ignores the upper right triangle because those are duplicates. It does include 1, which is sort of useless information because obviously something is perfectly correlated with itself. But here we go. We've got 3 correlations. The one we already found, productivity and job satisfaction, is 0.4797. The link between satisfaction and affect is 0.85. It is actually strong. It's not that strong. These are made up data. And then we've got productivity and positive affect, a slight negative link, which that's not what we would expect. But these are made up data, so don't read into it. Now, what if you want to know if a particular correlation is significant? Well, you could compare these to critical values in a table, but one way you can do this is actually if you, let's just focus on job satisfaction and productivity. So is this correlation significant? We can go back to this data analysis tool pack and go down to regression, say okay. Then we need to choose one that's our outcome variable and one that's our predictor. Let's say we're trying to predict productivity using job satisfaction, because there is a positive link between those two, or there should be. Okay, so I've highlighted the cells. The way I did that is I clicked on this arrow and whatever that is, some kind of arrow, and then just highlight all the ones I care about. Notice I have included the label, and I'm going to specify that again. I want to make sure it knows that first one's a label. And then let's just run with that. So let's say our output range, let's make it pop this up down here. Okay. So what do we get? So we knew the correlation would be 0.4797. We see the same thing. It's calling it something different because it assumes we're doing multiple correlation, but the same result, 0.4797. And then you can ignore most of this, and you can look one of two places to find your p-value. Whoops, not there. One of these two places to find your p-value. It's going to be the same information. It's the significance of the test, or the p-value. And you can see, is 0.52 smaller or larger than your threshold if you're doing kind of that traditional null hypothesis significance testing. So if we're using an alpha of 0.05, this would not be significant because 0.52 is not smaller than 0.05. Your p-value is the probability that you would get a correlation at least this extreme if the true correlation were zero. So if the actual link between satisfaction and productivity were literally zero, we would still see a correlation to some extent, whether positive or negative, just due to random noise. But the p-value says, how probable would a result at least this extreme be if the true effect is zero? So if the p-value is smaller than your threshold, so like a 0.05 alpha level means you're willing to be wrong 5% of the time if the null hypothesis is true. So if it's smaller than that, then it's statistically significant, as we say, or in our case, our p-value is larger than that. So we say, not super surprising to see a correlation of this size when you've only got 4 data points. So yeah, not significant. Anyway, that's how you can get your p-value, your correlation, etc. Let's do it in SPSS. Okay, here we are. I'm just going to import this. We could just enter the values ourselves. I'm going to import it directly from the Excel file. So I'm up here to File, Import Data, Excel. You might be looking in Downloads or wherever you have the data stored. Here is the data that I'm using. This is that spreadsheet that we were working in a minute ago. So I just say Open it. Then I can say, okay, ignoring most of what was going on right there. And here is what we get. Okay, so all the same information. Sorry, I'm not really a super SPSS user, so I don't know if there's a way to make this bigger. It's so hard to actually see what we're looking at. Okay, so I'm sorry, just squint or like hold it close to your face. But these are the same scores in the for the 3 variables. Now to correlate, I probably should set this one equal to a scale, like productivity and positive affect, but I'm just going to run with it because I don't think it's going to matter. To get a correlation, let's just go straight to the correlation matrix. So we'll say analyze, correlate by variate. By means 2, variate means variable, so 2 variables. So this is going to give us a lot of correlations between pairs of variables. It pops up this box. It wants to know what data we care about. So we say job satisfaction, productivity, and positive affect. Throw them all over here. If you want anything else, like you want some descriptives, you can get that. If you wanted to do a different kind of correlation, like maybe you wanted to correlate the ranks of the variables instead of the scores themselves, the ranks of the scores, then you could use Spearman, but we're going to use the Pearson product moment correlation coefficient, which is kind of the standard one that we're often thinking about. And let's say to tell test of significance, let's make it only show the lower triangle, kind of like Excel. We don't want to see all those duplicates probably. And let's omit the diagonal because it tells us no. This flag significant correlations, it's going to give us little asterisks. next to any significant correlations. So we hit OK, and it pops up the result, which is right here. We have a correlation matrix, and these are the exact same. Let's just make sure. Let's make sure we're getting our same information as last time. We were expecting 0.479, so that's right here, 0.48 once we round up with a p-value of 0.52. That's the same thing that we found a minute ago. So it's doing the same thing. Okay, and then 0.852, that's this correlation. Negative 0.05, that's this correlation of negative 0.0499. Okay, and so you can see the correlation, the p-value. Sig is for significance for a two-tailed test, so that means your p-value. And then n is the number of data points that went into each particular calculation. So that's how we can do correlation, get a correlation matrix, and even find out whether the correlations are significant in SPSS. What if we're working in R? Okay, so kind of the first thing we need to do is make sure we've got the right working directory. There are other ways to do this. You could just grab whatever you want from another directory, but I like to work from a particular directory. It's just how my mind works. So I'm going to see where am I at right now. Get WD, this means get working directory. And you could, one way to think about your working directories is kind of like your file explorer if you're in Windows, where you can kind of click around through different folders. So right now, this folder is in this PC, Windows, and R. That's what I call this. So if I use this command and to run it, I can either highlight it and click run, or I can just hit Control Enter or Command Enter on a Mac. And you can see my directory is this R folder. So I'm right where I want to be. If I were not in the right place, I would have to say set working directory, and then I would input where I want it to be. So I can do that right now, but nothing's changed. I was already where I needed to be. Now I like to read in files through Excel a lot of times, so I use a library called Read Excel. We like our puns in R, so you can see right here, Read XL. If you don't already have it, make sure to install that package using the install.packages command, and then put the package name in quotation marks. But then when you only have to do that once. Once you've got it, you can then sort of queue it up for a given session of R using library, open parentheses, and then the name of it with no quotation marks. Or at least they're not necessary. Okay, so let's do that. Let's run read Excel. Now, what this does is it gives me access to this function, read_Excel, and I want it to grab that spreadsheet, which is called what? I don't remember what it's called. It's right here. I'm just going to highlight the whole name, copy it over. Oops, need to put this in quotation marks. So now when I run this, it's just going to give me the information from that spreadsheet. It takes the Excel file and it puts it into what's called a tibble, which is like a kind of a super useful table. But you can see it's kind of doing many of the same things as you saw in tabular fashion in Excel and SPSS, where we've got all of our columns and our rows, and it's all the exact same information. Now, I don't want to have to run this over and over and over. So from now on, I'm going to say data is equal to that. So from now on, I'm assigning data to this. So what this means is after I run it, from now on, when I say data, I just say, what is that? Run data. It does this. It pulls up, it produces this tibble of the spreadsheet data. So now data means go look in that spreadsheet and grab all the data. Okay. If I want to grab a particular column, I can use the $ to grab a column. Like if I just want job satisfaction, I can say data $, and then I selected job satisfaction. Now when I run this, I get 73410, which we knew that's what we'd get in the job satisfaction column is 73410. So if you read what this says is data means read this Excel file, and then the $ says specifically that job satisfaction column. So data $job satisfaction means this vector of data right here. Okay, let's correlate that vector with the productivity vector. Okay, so I can use the correlation function, COR. What it wants as input, its first argument will just be one of your variables. Its second argument will be your second variable. So I've got job satisfaction, then I'm going to say comma. Now think about it. How am I going to access that productivity variable from this spreadsheet? I'm going to say data, which means go look in that spreadsheet. Specifically look at the productivity column, okay? Close parentheses. And then we run it and we get 0.4797, which is the same result we got in SPSS and Excel. We can modify this a bit if we want more information. We can say core.test for a correlation test. Now when we run that, we get lots of fun things. We see our degrees of freedom. We get that p-value, that 0.52. That's what we got in SPSS and Excel. These are different approaches to doing the exact same thing. Okay, and you get your correlation again down here. So if you want a more verbose version with p-values and a t-statistic and even confidence intervals for what basically -0.9 to basically 0.99. So we have a pretty large margin of error here. Not very confident since we only have 4 data points. Let's see. Okay, let's also get that correlation matrix, and that'll end the video. So we can use correlation function. Now, if we just put in data, it will take every single column and correlate it with every other column, including the person column. What was that all about? Quick reminder. We have a column that just says person 1, 2, 3, and 4. So it's kind of silly that we would correlate the order in which we put them into the data set. Why would that correlate with productivity? So that's what that would do. We don't want that. We specifically want correlations between job satisfaction, productivity, and affect. So I'm going to say specifically using brackets, I'm going to say go into this spreadsheet and then find correlations between the second through the fourth columns. This is column 1, column 2, 3, 4. So 2, 3, and 4. That's what we want correlations for. We run that. We get a correlation matrix. It does have the diagonal of 1s, and it does duplicate in the top right. There's ways to get rid of that, but this is kind of a quick and easy way to get a correlation matrix. And you can see 0.4797 for productivity and satisfaction, 0.85 for satisfaction and positive affect, -0.0499 for productivity and affect. So it's all giving us the same information at the end of the day, at least with these pretty straightforward statistics. Okay, so you've got what you need to calculate correlations. There are other things that you might want to take into account. Like, for example, you would need to carry out these procedures a bit differently if you had any missing data. But for the purposes of this straightforward video, that's all I'm going to cover. All right, there you go. That's it. Have fun.